Lesson 2. NDT in Industry. Why is NDT necessary? Since the early 1920s, the art of testing without destroying materials has developed from a laboratory curiosity to an indispensable tool to apply in a variety of industries, including fabrication, construction, manufacturing, and maintenance. Over the last 100 years, NDT has matured considerably as an invaluable service that can directly or indirectly benefit industry and the public in a number of ways, such as ensure product integrity and reliability, minimize failures, prevent accidents, and save human lives, control manufacturing processes to maintain desired quality levels, attain and sustain customer satisfaction and manufacturer's reputation, aid in better product design, lower manufacturing costs, and ensure operation readiness. Engineering demands for sounder materials. Another justification for non-destructive tests is design demands for materials that have fewer inherent discontinuities. As size and weight decrease and the safety factor is lowered, more emphasis is placed on better raw material control and higher quality of materials, manufacturing processes, and workmanship. NDT is frequently called on to confirm delivery of this new quality level. Public demands for greater safety. Public demand for the assurance of safe products has been receiving increased media attention, which is helping to prevent future incidents. Many new safety features and products have arisen due to concerns about personal injury and the environment. This public demand for safety is backed by organizations such as the National Safety Council, Underwriters Laboratories, Occupational Safety and Health Administration, Federal Aviation Administration, and others. Rising costs of failure. Aside from awards to the injured or to estates of the deceased, or costs to the public such as evacuations caused by a chemical leak, there are other factors in the rising costs of mechanical failure. These costs are increasing for many reasons, including greater costs of material and labor, greater costs of complex parts, greater costs because of the complexity of assemblies, a greater probability that failure of one part will cause failure of others because of overloads, and the probability that the failure of one part will damage other high-value parts. Also of note is possible part failure in integrated automatic production machines, shutting down an entire high-speed production line. In the past, when production was carried out on many separate machines, the broken unit could be bypassed until repaired. Today, one machine is often tied into the production cycle of several others. Loss of such production is one of the greatest losses resulting from part failure. When and where is NDT used? NDT is most commonly used where component failure may have catastrophic consequences, such as in airplanes, electric power plants, petrochemical plants, gas transmission lines, offshore drilling platforms, and ground transportation systems and structures. The primary use of NDT can be broadly classified into two categories. 1. New parts manufacturing, and 2. In-service applications. New parts manufacturing. New parts manufacturing is the testing of products through the manufacturing process to ensure the parts comply with design specifications, from testing incoming raw materials to the final acceptance of the product. NDT is applied systematically at various stages in the manufacturing process. It is used to process control to ensure that the item meets the acceptance criteria established for each stage of an item's development. This process starts with the selection of raw materials and continues through to final assembly. Early detection of discontinuities reduce costs associated with scrap and rework and avoids the costs of returns and customer dissatisfaction. In-service applications. In-service applications comprise the periodic inspection of items that are involved in some type of ongoing service to determine whether the items are suitable for continued service. The advantages of NDT for in-service applications include early detection of potentially dangerous and costly unscheduled service interruptions and the ability to monitor degradation processes from which realistic and cost-effective reinspection schedules can be developed. The extent of which a part's strength or service life is affected in a specific service environment by the presence of a given discontinuity cannot be readily estimated. Because cracks tend to increase in size in many service environments, the early detection of cracking may require the corrective action of scrapping the item. Where is NDT used in industry? NDT can be found in almost all professions and industries where material quality control or the testing of in-use products is required. The most prominent of these industry sectors are manufacturing, petroleum chemical or petrochem, aerospace, maritime or marine, construction, military, and power generation. Manufacturing. Material quality control of the testing of in-use hardware is crucial to ensure that the products meet design specifications. NDT inspection points are typically found in raw material testing, forging, casting, machining, welding, and fabrication. Manufacturing of nearly all products requires non-destructive testing. The extent of non-destructive testing depends on the complexity of the end product and the acceptable risk. The petroleum and chemical sector. This sector uses non-destructive testing to validate the safety of piping, storage vessels, and refineries. The non-destructive testing applications in this sector minimize erosion and corrosion failures through monitoring of structural wall thicknesses and weld integrity to keep dangerous chemicals and petroleum products within their containment systems. Aerospace. Discovering discontinuities and monitoring their growth is paramount in in-service inspection of aircraft and spacecraft. Scheduled periodic NDT of airframes and engines is vital to ensuring the safety of passengers and cargo while simultaneously lengthening the intervals between repair and replacement. The aerospace industry requires precision non-destructive testing that requires a high-level probability of discontinuity detection to increase safety. Maritime. NDT in the maritime industry includes commercial diving, oil rigs, ships, and underwater pipelines. Construction. Non-destructive testing is routinely called upon in the construction industry to validate the quality of buildings and highway infrastructure, including bridges. Testing of weld quality and concrete quality and the cure state are the primary construction NDT applications. The cure state of concrete refers to the amount of compressive strength the concrete has achieved throughout its curing cycle. Often when you place concrete, when it's in its mobile state, we consider that its plastic state, where it's flowable. And then once it starts to set up and cure, we call that the cure state. Now, typically concrete meets 75% of its compression strength within 7 days of being placed. And it doesn't typically reach its full cure state, meaning its compressive strength, for approximately 56 days. So various types of non-destructive testing methods can check that concrete's cure state and determine where it's at in its curing cycle. The military sector. The United States Armed Forces utilizes non-destructive testing to maintain weapons, for procurement first article testing of newly manufactured items, and to validate ammunition quality. In addition, what a lot of people don't recognize is that the military also controls many parts of the infrastructure within the United States. For example, the United States Army Corps of Engineers, which is part of the U.S. Army, controls a lot of hydroelectric dams within the United States. So there's a tremendous amount of non-destructive testing used with the verification of the fabrication and the in-service status of various dam components and structures, steel gates, navigational locks, and things like that. So we're talking about where NDT is used in the military. It's not just for weapon systems and ammunition quality. It's also for a lot of other elements that are part of other industries such as infrastructure or construction or maritime. Power generation. Power generation requires non-destructive testing to keep power turbines running effectively. Power turbines, which are typically powered by gas, nuclear, wind, water, or steam, require frequent and planned NDT to keep electrical power flowing to customers. Some less obvious uses of non-destructive testing include the use of non-destructive testing to verify the original fabrication and the in-service quality of amusement park rides. When we look at amusement parks, they're fairly complex structures. When we look at roller coasters and many of the amusement park rides, that safety is a huge concern. So let's just say Disney, for example, they have full-time non-destructive testing technicians that are constantly going over all their amusement park rides to make sure that there is no fatigue or potential failure with any of their amusement park rides. Research and development projects. There's a lot of laboratories out there that are constantly doing non-destructive testing in a research or development capacity for developing of new products or new ways to perform NDT or to verify new ways of performing quality control on various objects. And also the railway system. There's a tremendous number of railways that are in the United States, and all of these railway lines are required to be inspected on a very routine basis to make sure that the track systems are operating as they should be and there hasn't been any structural damage. So there's a whole industry of NDT techs that ride on very small rail cars, essentially independently down the tracks, that will automatically ultrasonically test the rails that they are riding on, checking for any in-service defects. Non-destructive testing methods. Today, the visual testing method is still the most widely used, but is supplemented by a vast array of additional non-destructive tests. The most widely known physical and chemical means used to investigate the composition of test parts rely on sound waves, electrical currents, magnetic fields, radiation, thermal waves, and tracer liquids or gases directed into, and in most cases, to penetrate the materials being tested. NDT has been adopted by many technical and regulatory agencies to evaluate an item's ability to meet in-service performance expectations. The assumption is that if an item is free from unacceptable conditions, it should meet performance expectations, that is, carrying loads, withstand vibrations, or maintain dimensional integrity. The technology has matured to the extent that some methods have become standard practice. The selection of an appropriate NDT method for specific applications is based upon the physical characteristics of the material. For example, whether it's magnetic, metallic, massive in size, or if it's irregularly shaped, and the discontinuities of interest, including probable location, orientation, size, and morphology. Test parts with simple structures and geometries are easier to analyze than those containing complex configurations. Large, singular discontinuities are easier to detect and assess than distributed collections of small discontinuities that may extend over a large area. The NDT technique selected for inspecting a part or component is unique to each material and service application. NDT may be done in a cursory one-step manner for screening purposes, or it may use a multi-step process for reaching detailed conclusions regarding material conditions. This scanning may be performed at sensitivity levels that significantly exceed those that are used to eventually evaluate the severity or potential significance of each discontinuity. The American Society for Non-Destructive Testing currently recognizes 16 different non-destructive testing methods. They are, in alphabetical order, acoustic emission testing, abbreviated AE, electromagnetic testing, abbreviated ET, ground penetrating radar, or GPR, which there has been talk about removing this as a non-destructive testing method under the guise of the American Society for Non-Destructive Testing, only because most ground penetrating radar isn't performed by non-destructive testing technicians. They're typically performed by construction material technicians in more of a geotechnical capacity. So it's not really in the realm of what we typically consider as non-destructive testing. So there's been talk about removing ground penetrating radar from the list. Number 4 is the laser methods testing, which is a fairly new NDT test method that's really kind of in its infancy as becoming a well-used common test method. It's abbreviated LM. Then we have leak testing, LT, liquid penetrant testing, or PT, magnetic particle testing, MT, magnetic flux leakage testing, or MFL, microwave testing, MW, which, like the laser method testing, is a fairly new non-destructive testing method that is becoming more popular in the various industries. It has some pretty significant limitations, however. Number 10 is radiographic testing. 11 is neutron radiographic testing, or NR. 12 is thermal or infrared testing, IR. 13 is ultrasonic testing, UT. 14 is guided wave testing, or GW. 15 is vibration analysis, or VA. And 16 is visual testing, or VT. Now, of these 16 methods, the most commonly used are electromagnetic testing, liquid penetrant testing, magnetic particle testing, magnetic flux leakage testing, radiographic testing, ultrasonic testing, and visual testing. Now, throughout any non-destructive testing training program, you'll hear the term method and the term technique. So what's the difference between method versus technique? The term method is used to describe a collection of inspection techniques. This classification system is useful because a method is defined by the probing energy that is used, whereas techniques are ways that the probing energy is applied or detected. Probing energy and materials used in non-destructive testing include electromagnetic waves, mechanical vibration or waves, particles, and liquids. So for example, you may hear the term probing medium. That's commonly thrown around in the non-destructive testing arena. What that means is, what is the type of energy that is being imparted on the test object that we are looking to have any potential discontinuities interrupt that medium, giving us some type of a signal or indication that there is something within the part. So the ultrasonic testing method uses sound waves, or really they're mechanical vibrations that are in the part. So when the ultrasonic test is performed, we introduce a sound wave or mechanical vibration that travels through the part, and if it impacts a discontinuity or something within the part of that mechanical vibration returns back to our test system, our transducer, giving us an indication that there is something within the part. Other types of non-destructive testing methods use different types of probing medium. Radiography, for example, uses radiation that passes through the part, and there's an interference if there's any type of discontinuity within the part that gives us an indication that we have something within the test object. Magnetic particle testing, for example, uses magnetic fields that travel through the part. Liquid penetrant testing doesn't really use a probing medium. Instead, what we do is we have a colored dye that will seep into any surface breaking type indications, and then we draw that dye out using what's called a developer that gives us a visual indication on the test object. So there's lots of different NDT methods, and they use different types of probing medium. So that's kind of how we break down the methods, is the type of probing medium that is used. Now, as an example, in the ultrasonic testing method, where the probing energy is high-frequency sound waves, meaning they're mechanical vibrations, the UT method includes single probe techniques, dual probe techniques, tests where the probe directly touches the test object or where the test object is immersed in water, and many other variations of the technique. But they're all using the same type of testing medium, probing medium. Now, there are some times when the same probing medium is split between two different methods. And what typically happens there is when we have a test method, ultrasonics is a great example, where we're using sound waves. Well, if we have a technique that is diverging far enough away from the primary method to where it almost needs its own type of training and it needs its own classification, then it will separate out. A good example is acoustic emission testing, where acoustic emission testing uses sound waves as well. It's very similar to ultrasonic testing. The difference is that instead of transmitting a sound wave and waiting for a return signal to come back, we have a probe that will be mounted permanently to, say, a bridge. And if a crack were initiated, that cracking sends a sound wave out throughout the structure, and it's picked up by that probe that's permanently mounted. Now, we're using the same concepts as ultrasonic testing, but it's used in such a unique way that it was determined by ASNT that it really needs to be considered its own method. Even though the probing medium is still sound waves, it's different enough from conventional ultrasonics that we're going to classify it as its own method. Guided wave testing is another example, using sound waves. With guided wave, we are transmitting sound through a pipe. Let's say it's typically used on pipelines, where the wave will travel along the surface or very slightly subsurface from the on the material's wall itself. And if there's any break in it, then it will return back. But guided waves use waveforms that are different enough from conventional UT that it was determined to break that out into its own method. So, in a nutshell, a method is a type of probing medium, and they usually keep them all together. But when that probing medium or that technique, I shouldn't say technique, the method differs enough from the original method, they'll break it out into their own method. Radiography is a good example. Conventional radiography uses gamma or X radiation as its probing test media. Neutron radiography uses neutron radiation. Now, gamma and X-ray compared to neutron radiation act very, very differently. So even though the probing media is still all radiation, neutron radiation is so different from gamma and X radiation that they separated neutron radiography out into its own separate method. Now, when we're talking about a technique, like we mentioned here with ultrasonic testing, another way to kind of explain it is magnetic particle testing. So with magnetic particle testing, the ultimate goal is to magnetize the part and look for any leakage fields, that we call it, caused by an indication. Now, we can introduce that magnetic field into the part in many, many different ways. And how we introduce the magnetic field into the part is typically considered a technique of magnetic particle testing. For example, a coil is an example of a technique for magnetic particle testing versus a yoke or a prod or a central conductor. Those are all considered techniques within magnetic particle testing. And you'll learn more about these techniques as we start talking specifically about these NDT methods. But that's the difference between a method and a technique. And that concludes this lesson.